Okay, everyone. Thanks so much for being here for our second talk of this three talk afternoon series. So, as someone who's worked in machine learning, and for any of you guys working in machine learning, you may know that the two most feared words can sometimes be in production. So I'm personally really excited for this one because LLMs haven't existed for too long. So, learning about from Emeli Dral how to put them into production should be a really fascinating topic. So, welcome.
Thank you. Thank you so much for such a nice introduction. I'm really happy to be here today, and I believe, well, monitoring is boring, like everyone prefers to raise or train models, not to monitor them, but I believe we'll enjoy some information about how we can actually set up monitoring for NLP and large language models in production. Just a brief introduction. My name is Emeli. I'm co-founder and CTO of Evidently AI, which is a startup where we build open source tools to monitor, validate, and test machine learning models, of course, including large language models. And prior to that, I worked as a data engineer to help companies train, deploy, and monitor machine learning models. So I will rather speak from that experience, again, during the deploying models myself. Well, we all know that train a good model, including transformer, is a quite tough task by itself, and then we need to deploy it to production, which also is not that obvious, but unfortunately our job doesn't stop there, right? We need to make sure that our model is safe and sound and produce valuable data, valuable output, because, well, when we use some model in production, each failure costs us something, so we need to make sure that everything works. Well, luckily, we have years of experience of having software solutions in production, so pretty much we can reuse quite a lot of monitoring architecture from the standard services. There are a lot of metrics like service health, uptime, memory usage, latency, etc., which we definitely should track for our machine learning-based services as well. But here we have extra layer of complexity, because we need to also monitor for data health, monitor for models quality, and look for metrics like data drift, model quality, depending on the problem statement. Well, it's quite a lot. And when it comes to LLMs, it's also quite a lot of things that we need to look for. For example, there can be quite a lot of technical errors, like wrong encodings, or maybe unexpected language. Maybe there are some technical bugs in our data processing pipelines, or maybe there are just some data shifts because our models are not live in the vacuum, right? There are a lot of things that can change outside, and there might be new topics, or maybe the change of the shares of different topics, so it's very important to track it as well. Pretty often, especially when it comes to using of transformers, we use some third-party models through the APIs, and it's pretty important to check for model behaviors, because if this model has been retrained, for example, or updated, then probably you can face some issues on your subset of queries you use this transformer for. So it's pretty important to track for model behavior shifts. And, well, model attacks are quite interesting and popular nowadays. So sometimes you face things like prompt injections or some other serial use. This is why it's quite important to keep track on our models. And, well, hallucinations is also a very well-known problem when our model produces some unrealistic output, and that's also not that good, right? So this is why we really care about models quality and data quality as well. So how to prepare? Again, monitoring, but we need to make sure that we have very clear vision and expectations of what we actually want to have from our monitoring. And, well, I believe there are quite a lot of expectations, but these three are quite important. First is meaningful metrics, because, well, nowadays we have a lot of tools which helps us to calculate like dozens or even more different statistics, but if you will track for all possible, let's say, statistics we can calculate on top of our raw data, we will be easily snowed under by tons of false alerts, and I believe it will be very similar to just not having any monitoring, because, well, if you have alerts every minute, I would say no one really cares about them. So it's pretty important to select only meaningful metrics. The second thing is alerting policy. It's very important to define right thresholds for each metrics and very clear action policy. It can be very different things. For example, we might want to send a specific object to the manual review, or maybe fall back from machine learning model to some other system, for example, rule-based, or maybe trigger a training process. Sometimes we maybe want just to send a message to our data engineer with some data and some statistics to potentially fix the issue later. But it's very important to have this connection between the metrics and action policy. And finally, when we, for example, deal with large language models, sometimes it's not that obvious how to react to different metrics beyond the thresholds. And this is why it's pretty important to include enough information in our alert. I mean, to provide some context which will help to figure out what's going on with the model and potentially fix the issue faster. So this is why context with a lot of, maybe not a lot of, but with some statistics and some visual information like maybe distributions is quite important to solve issue faster. At least pretty often we might save some time from our data engineering team to grab some logs and calculate all the statistics ourselves. So it's like meaningful metrics, action policy, and enough context. Well, having this in mind, let's start to discuss what actually we can monitor for our machine learning models, especially large language models. So I would say that in case you're lucky enough to have a direct signal which tells you how good your model is, it's better to start from it. I mean, if you have, for example, immediate feedback and you do not need to wait to get your delayed feedback, then you can pretty fast calculate any quality metrics which is relevant to you. For example, like precision, recall, maybe mean absolute error, whatever makes sense for your problem statement. But unfortunately, it happens pretty rarely, and in many cases we just do not have this direct signal without any time delay. And unfortunately, we need to come up with some other metrics, and here we have some proxy metrics. In most cases, the data quality metrics do really help because, well, if there is something wrong with the data, then probably the model might react somehow unexpectedly. So it doesn't necessarily mean that we will have some problem with the model's output, but potentially we will. So data quality is very important. And luckily, the input data is something we always have at hand, right? And this is why it's quite important to calculate some data quality metrics. And I'm going to expand on this topic a little bit later. Together with input features, we always have the output of our models, right? Without any, almost without any delay. And in this case, it makes sense to analyze this output as well and calculate things like prediction drift, for example, or other types of model output drift. It helps us to see whether there are some unexpected shifts and maybe trigger some alerts to manually check what's going on. Well, proxy metrics are very important, and when it comes to large language models, I believe it's a little bit more complicated compared to direct signal. This is why I'm going to focus on proxy metrics more, because when it comes to direct signal, I believe anyone know what to calculate. So how to deal with unstructured data? Just to start from the structured data, when we have some tabular data, we can easily analyze each individual feature, right? We can calculate something like share of missing values. We can calculate tones of metrics about some range violations, especially for numerical features. For categorical, we can calculate the proportion of different categories, check that the main category is exactly what we expected, compare distributions to calculate drift. So it's all pretty well-known techniques which we can use to make sure that our data has good quality. But when it comes to unstructured data, it's not that straightforward, right? So we need to somehow preprocess those data to make sure that we can analyze it for data quality and data drift. So, well, pretty often we even deal with multimodal data, especially when it's the data sets related to, for example, products review or chats or maybe some support tickets or complaints. We definitely would have raw text there, but together with raw text, we will also have some data related to things like maybe countries from where the query comes, or maybe iteration system, product category, a lot of different structured data which are pretty valuable, and definitely we want to keep both unstructured and structured data in our data set. So this is why sometimes we need to design the monitoring for multimodal data sets as well. So now finally to monitoring. So what to monitor for unstructured data? Well, today I'm going to introduce to you 3 main strategies, which I believe works well in practice. And finally, quickly touch a point about multimodal datasets, because I believe sometimes it's also quite important. So those 3 main strategies, there are more strategies, of course, but I believe these 3 works really good. So first is monitor raw text data if you have access to such data. Second is create some descriptors. And finally, we can monitor embeddings as well. And let's go through them one by one. So first is monitoring for raw text data. Well, for raw text data, we can build quite a lot of things, but I would like to underline 2 main topics which I really like. The first is model-based drift detection, because for raw text we are lucky enough and we can build very well binary classification model based on the back of words text representation. And this is really cool, because if we use the back of words features based on our text, then we can train any interpretable model. For example, it's well known in the industry that binary logistic regression is very good for text, right? And if you train this model to distinguish between the reference dataset, and the reference is the dataset where we are happy with the model quality. For example, we can handpick this dataset with respect to our problem statement and maybe the main area specifics, maybe handpick some queries, maybe some specific text, or just take the dataset from the validation phase, and we can compare this dataset to the new batch of data. For example, the one we collected during the day. Right? And well, what we can do, we can definitely build the binary classification model. Then if we use logistic regression, we can check the words with the highest weight, and it will give us a lot of intuition about what's going on. So what is the source of the differences from our text? For example, if in the current dataset we see that there are a lot of words like disappointed, or sad, size maybe, and when it comes to reference data set, we see some words like stunning, perfect, compliments, lovely, then probably the drift, the difference of our text comes from the sentiment, not from the text size or maybe new additional topics. Well, that's questionable, but still we can create a lot of hypotheses of what's going on. This is why I like this way to calculate drift on top of raw text really well. And luckily, logistic regression really works good. So in this case, as a metric score, it's good to use some quality of your model. And I would say something like receiver operation curve, area under the curve works quite well. But just make sure that you created a very good threshold. Because, well, we need to come up with the threshold, what is a good model and what is a bad model. I mean, what is model is confident to distinguish between reference and current dataset. Does it mean that we need to have our area under the curve just higher than 50% or something else? So it depends, of course, on the frequency of alerts you want to get because of the text drift. And there is another way how you can potentially do it. And instead of binary classification model, you could use topic modeling to track what are the topics in your texts. I would say it's a little bit more tricky because, well, we know that I would say all unsupervised, pretty all unsupervised problem statements are incorrect from the math point of view, right? Because there are no correct solution, and we cannot say what is the right structure of our data, right? We cannot tell what are the right topics. This is why you would probably spend quite a lot of time into getting the right clustering model, which makes sense from the problem statement point of view. And well, but if you're ready to invest some time into building such model, you can then apply your clustering model to a new batch of texts and just track the topic you have, the topics I mean. So you can compare the sizes of topics, you can track for new topics, or maybe track for some topics you lost, and this is how you can treat your drift. Good news is that if topics are meaningful, then you still can generate some insights of what's going on and what has changed in your text. So this is why I really like to use the raw text for monitoring, because you can easily come up with good ideas of what's going on and potentially fix some problems faster. So that's, I believe, the most interesting things we can monitor on top of the raw data. The second strategy is to turn unstructured data into structured, and it works just wonderful for text. Why so? Just because if you have an access to the raw text, you can basically calculate a lot of statistics. We can calculate text drift, text length. We can calculate the share of out-of-vocabulary words. We can apply some sentiment models to each object, each raw text. And by doing that, we actually can create some descriptors which are quite similar to just numerical or categorical features. Like, for example, if you have a pretty specific problem statement, for example, you use some transformers like GPT to produce some output, you might want to create very specific transformer. For example, you might want to check whether the output from your transformer is correct HTML, or is correct Python code, or maybe is correct JSON, right? And this is also a descriptor, because basically what you do is you apply your text. Let's say you first create a prompt automatically, then you send it to transformer, then you receive the answer, and you just check with some third-party methods whether it is correct JSON or not. And the result of such check is the binary feature, binary descriptor, just true, false, correct JSON or not correct JSON. And by doing that, you create structured representation of your text. And as soon as we have some structured representation, what can we do? We can basically track any metric you like. So that's the example how it looks like in Evidently. So basically that's a dashboard, and the idea is super straightforward. Now you have numerical and categorical values, and you can come up with any rule-based checks, for example, you like. For example, min-max ranges for text length, or maybe some expectations of share of non-letter symbols on OOV, or maybe share of non-correct JSONs from the output of your model. So whatever you like, and now it's like structured data. So we can use any method we can use for numerical data or categorical one, like correlations between, for example, some descriptors and the target. We can track drift, right? And it's also will be very insightful, especially if you invested enough time into building and calculating the right descriptors. So finally, when it comes to embeddings, it's quite hard to create something good from the interpretation point of view because, well, it's embeddings, unfortunately. But we still can do quite a lot of nice things. For example, we can treat embeddings like objects, process text like an object in high-dimensional space. And having this in mind, we can use a lot of distance-based metrics to calculate the drift. Like, for example, what we can do is, we can take the vectors from the reference dataset, then average them to get a single vector. Then we can do the same for the current dataset and just calculate any distance metric between those two vectors, like Euclidean, cosine, whatever you like. And this will be your aggregated estimation of drift. Of course, no interpretation, unfortunately, but it will be a numerical value you can track and see whether it's increased or decreased, or maybe with help of experiments, you can even set up a good threshold for this. And finally, there are some more methods which we can apply to embeddings. For example, we can also build a domain classifier, which will try to solve binary classification problem and distinguish vectors from reference and the current. Well, no interpretation, unfortunately, but still the quality of the model will tell us what is the confidence of the model for separating between the reference and current data, which is also quite good. And finally, there are some engineers who prefer to calculate the share of drifted components of embeddings. Again, it's quite hard to interpret them, because how to interpret that fifth component of our embedding has drifted? Well, nothing, right? But at least we can check the share of drifted components, and by having this value, somehow communicate the confidence that we do have data drift in our embeddings. So that's also quite interesting. And finally, I would say a couple of words how we can deal with some multimodal data. And here, the strategies will be very similar to what we just did for the text. So we can either split data by type, turn all the data to unstructured, or turn all the data to structured. So I believe that's the most practical ways to solve it. So first is really straightforward. For example, if you want to calculate data drift for your multimodal dataset, what you can do is to, for example, calculate the drift for each individual feature from the structured part of your data, then calculate drift with help of, for example, binary classifier for your text, and then calculate share of drifted features, right? So that's how you can process it separately. And of course, well, pretty same goes for other metrics. The second strategy is to create somehow a joint structured data set which contains only numerical, categorical, maybe some binary features, but it's also categorical, so yeah, that's what we can do as well. I do really like this method because by doing that, you need to preprocess your raw text. It will give you some descriptors, and descriptors are structured data, right? It's also a table. Basically, this means that you can join your descriptors to the features and work only with structured data. And here again, you can use a lot of statistics like missing values, some maybe range violations for numerical features, share of specific categories, data drift, and whatever you need on top of your joint representation of dataset. And well, descriptors are very meaningful because you know what each descriptor means, so it's very good to interpret what has changed. Third strategy is to try to move you from multimodal dataset to the unstructured one. I don't know why I call embeddings unstructured, just because it's hard to interpret them, I would say so. So in this case, I would suggest to imagine that our structured part of the dataset, like those metadata, are like additional components of the embeddings. So it will basically move us to the more high-dimensional space where we have some additional components, right? So, and in this case, we can just join our embeddings with our features and try to use, for example, binary classification model to distinguish between the reference and current dataset. So from this point of view, we will be able to get this aggregated estimation of the confidence that there is a drift, but you will lose some interpretation, unfortunately. But that's the cost of having the integral estimation of drift for the whole dataset. Well, just final words about the model's output, because it's also very important. I personally believe that the model output drift is a very strong signal of potential problems with your model. So when it comes to structured output, like labels in case of classification problem, or maybe a numerical value if you solve regression problem, we all know what to do. We just need to select the suitable statistical tests, or maybe distance metric, probabilistic distance metric, of course, and just evaluate the difference between the distributions. But what if our output is also unstructured, like, for example, text from the transformer? In this case, we also can monitor the drift, because we just discussed that, for example, we easily can create some descriptors and check for drift in descriptors, right? And I would really, really suggest you to start from this part of monitoring if you just started to work with large language models, because the drift in input data is, let's say, less predictable in terms of the potential major issue with the whole model compared to the output drift. So the output drift is a very good start to monitor the quality of your unstructured data. So, well, summing up. Monitoring is something we really need to implement when we have production services. I believe that's pretty straightforward. But even if you have some unstructured data like text, you shouldn't just ignore this part of data in your monitoring, because we actually can do quite a lot of things. When you have raw text data, we know what to do. We can build domain classification model or calculate some descriptors, and it will be so good in terms of interpretability. So I would really suggest to do that. You will immediately see what exactly has changed in your data. If you're dealing with embeddings, which is quite often the case, well, in this case, we also have some distance-based models. no interpretability, but at least numerical estimation of the drift size. And finally, if you have a multi-model dataset, I would suggest to move this task to one of the following. Either go to embeddings and calculate drift using some distance metrics, or go for descriptors and create the joint structured representation of your dataset, and then calculate quality metrics and the drift metrics, which works for your dataset. So basically, that's all I wanted to share with you. I believe you're in time. And yeah, happy to answer any questions or just discuss anything.